if you turn your exam preparation sheet over, you have this now, what we're going to find is that an inductor acts exactly the opposite as a capacitor. You remember that for a capacitor, the voltage across the capacitor depended on how much charge was in the capacitor. And when it was empty, when Q was 0, it acted like a what? Like a 0-volt battery or a wire. Later, when the capacitor is full, it acts like what? Like an open switch. Okay. Well, we're going to find that this inductor acts just the opposite. Watch. Watch and be amazed. Okay. Now you remember with a circuit that had a capacitor, there were 3 times that I could answer questions. Right after I closed the switch when the capacitor was empty, a long time after I closed the switch when the capacitor was full, and then after the switch had been closed a long time, right after I open it again. Same thing's true with an inductor circuit. The same 3 times. Immediately after the switch is closed, a long time after the switch is closed, after the switch has been closed for a long time, and immediately after it's then opened. Those are the 3 times. Now, with the switch open, there's no current anywhere. Particularly, there's no current through that inductor. If I close that switch, I can change the current through R1 instantly. It goes from 0 up to 4 amps instantly. But I can't change the current through an inductor instantly. It's got to ramp up. So what's the current through an inductor? 0 amps. And so what's that inductor acting like? An open switch. Oh, the anti-capacitor. The capacitor acted like a wire when I closed the switch, and a long time after I closed the switch, it acted like an open switch. Well, an inductor acts like an open switch when I close the switch, the real switch, and a long time later, after it stops fighting, it acts like a wire. So, the magnitude and direction of the conventional current through the battery, well, the current, if it can't go through the inductor, has to go this path. And so V equals R gives me 200 volts pushing current through 45 plus 5, 50 ohms in series. And that's where I get the 4 amps up. And then that 4 amps would come down here, and that 4 amps would come down there, and the 4 amps would go there, and then back around. Now, what is the voltage difference across the inductor? Now, we've got this formula that gives you the voltage difference across an inductor. It'll be on the front page of the final. The voltage across an inductor is equal to minus L delta I over delta T. Don't you ever use that. Don't. If you try to use that, you're going to confuse yourself. The only time you can use this is when you're saying, oh, the I's not changing, so delta I is 0. So the inductor voltage is 0. Because I don't know how quickly I'm trying to change the current, I don't know how to use this formula. But I do know how to find the voltage across an open switch or an empty socket. What do?
Look away.
Look away from the sun. Don't look at the sun, look away from the sun. I've got 4 amps going through 45 ohms over there. V equals R. 4 times 45 is 180 volts. If there's 180 volts from here to here, there's 180 volts from there to there. So it would be 180 volts, and it would be oriented with the positive up to fight the current. Is this making sense? Is this feeling familiar? Now, the next part, B, is a long time after the switch is closed. Remember, if I plot the current through the inductor, I close the switch here, and it ramps up to its final value. Well, a long time means up here, where it's 40 amps, 40 amps, 40 amps, 40 amps, 40 amps, 40 amps. What's the change in I? 0. And so what is the voltage difference across that inductor? 0. What's it acting like? A wire. A long time afterwards, it acts like a wire. Now, if that is a wire, where's the current going to go? Is it going to go through R1 or through that wire? Through the wire. That means R1 is shorted out. That means all the current's going to go through the inductor, through R2, and back around. If I use V equals IR, now I've got 200 volts pushing current through, it's just going through R2. 5 amps. 5 ohms. And that gives me an I of 40 amps up. Okay? The voltage difference across the inductor is 0. It's acting like a wire. And what's the magnitude and direction of the conventional current through resistor R1? 0. It's shorted out. Now, folks, we have run out of time, but on Wednesday and Friday, we're just going to practice. We're going to see that these inductors act just the opposite as capacitors. See you on Wednesday, people.